Hi, everyone, and welcome back to VectorLab. Today we're with Eoin, who's a forward deployed engineer at OpenAI, and he's going to show us how to optimize your supply chain given new tariff constraints. Eoin, can you start by introducing yourself?
Hi, my name's Eoin. I'm a forward deployed engineer here at OpenAI. For those who don't know, forward deployed engineering is a new function in our company where we deploy on site with our customers to solve their biggest problems. I joined about 6 months ago, which was very early on in the days of forward deployed engineering. It was when we really started scaling the team. Before April, we had like maybe 2 or 3 forward deployed engineers, and now we're like a much larger team. So yeah, very excited to be on the show and talk through one of the problems that we solved.
Amazing. Thanks for the intro. So can you describe a little bit the problem we are going to discuss today?
Yes, so this is one that came up with some of our Asian customers in the manufacturing industry. So they were facing issues this year where, like, in the rapidly changing world of tariffs, particularly with the U.S. administration, meant that the price that the cost of shipping for them was changing like every single week, and they had to constantly update their supply chains to remain ahead of the competition. So we built a demo for them to show them how you could use Gen AI to help respond to these ever-changing scenarios faster than their competitors. So let me jump into this demo. Yeah, cool. So here you can see a map of a fake company called Wheelco, which is manufacturing a tire in Seoul in South Korea. If you look at what kind of parts we're bringing in for this, it's like, okay, so from China, we're sourcing tires, rims, and then the subcomponents for this are aluminium, steel, and rubber. For this scenario, we're going to imagine that there's a new 20% tariff from China impacting Korea, or tariff importing parts from China to Korea. As you can see, a huge amount of the supply chain involves importing from China, so this is obviously going to be pretty detrimental to the bottom line of this fake company. In addition to this, our lead time is also slightly longer than we want it to be, so this is something we might want to improve. So I'm going to pan over to the ops view, where we have a quick view here, which shows how we're currently tracking towards our targets. This middle section here is the proposal. Currently, we haven't made any changes yet, so this is empty. And then over here, we have this chat widget, which is what we're going to use to make our changes. This is powered by ChatKit. So let's quickly add to this tariff scenario and see how we stand. So let's describe there.
Is it the delivery, on-time delivery, or is it something?
Yes, on-time delivery percentage.
Got
So
it.
this is it's essentially the risk in the supply chain. So higher is better for this one. So currently there's an 85% chance of us meeting this 20% lead time, or 20-day lead time.
And the lead time being the time it takes for a product to be shipped and then received.
Yeah, exactly. Yeah, and assembled. And tariff importing from China to South Korea. How does this impact my plans? Press enter here and then wait for it to come back with a solution. So first, it's going to give us a very high-level view as to what this is going to do to our cost. We set a target here of $72. So currently, we're a little bit under, but not very comfortably under. So first, it's going to give us it's kind of identified our goal here and giving us a plan of how it's going to do it. So it's going to find the plan and then show a condensed summary for importing from China. As you can see here, with this current plan, we're importing a lot of components from China. It adds $8 to our cost, which is unacceptable given our $72 cost target. Let's now ask it if we can see some more details to understand in a more fine grain level how this is going to impact us.
So more details on the factories that are impacted? Yes.
Yes, exactly. So you can see here that, for instance, this tire supplier in China is impacted by the tariff, or tire supplier from China is impacted by the tariff, and it's going to add $1.53 to each unit. And then adding all of these up is how we get to our $8.70 per unit impact. So let's quickly add it as a constraint now, so that the model will try and improve the situation as best it can while keeping current weights intact. So let's add this supply. And now it'll go back and it'll give us our very first proposal, but this will be without any further optimizations. This is its very initial attempt. So you can see here now that it's fetched its current plan, and now it's just updating the model underneath the HUD to account for this. So you can see here that, okay, it wasn't quite as bad as the $8 that it suggested up here. This is because it's actually made some changes under the hood. So it's brought our lead time down to 15 days. This is likely because it's sourcing more things from within China and Japan, which might have quicker lead times anyways. So not quite as bad as $8, but now we're way above our cost target, which obviously we want to hit. So let's ask it, can we hit a per unit cost while keeping lead time at or below 17 days. So you can see here we have a little bit of flexibility as well. Like we currently have a lead time of 15 days. We could maybe sacrifice some of this lead time to get the cost target down. So now it's going to run this optimization. You'll see in a second the output of this and how it went about it. Essentially what it's doing under the hood now is it's running 5 different scenarios where it's varying the weights that go into this supply chain solver, and then using this to, and then it's going to take all the results from this and then look at it to figure out which one best meets our needs. Yes, if we give it a second here to come back with its results.
Just the difference between completeness and capacity on the... So is it completeness to have all the parts I need to build the finished product, and capacity it's more like how much am I able to produce per day? So maybe I have lots of parts, but I don't have enough people to build it. Is that the difference
Yeah,
between the two?
yeah, exactly. Completeness is you have enough parts to manufacture 50,000 tires, which is what this scenario is based on. Capacity is making sure that you're not running any factory above 100% of its output capacity, which would be unrealistic. So it's just putting some constraints on what the model is doing to make sure that it actually ends up being realistic.
Awesome. Thanks.
So you can see here that it came back with a few different variants. It identified one variant here where it's going to cost us $71, which is conveniently below the $72 cost cap, and it's going to take exactly 17 days. You can see here that it actually did find some other options, but it decided to select this one because it's got the lowest cost, and I said the lead time I needed was 17 days. If you want to take this a bit further, I can run this again with a more aggressive cost and lead time, which it probably won't be able to reach given the input data, but it gives a bit more of an insight as to how it works under the hood. So we can say, now can we target the same cost of 72 USD while keeping lead time at or below 15 days. So when we dive into what it was doing under the hood here, this will give us a bit more clarity into it. So for this initial 5 seeded optimizations, it just goes for a nice balance of cost, on-time delivery, and lead time. When you ask it to continue solving, it'll then kick off many more optimizations under the hood and start to hill climb in the direction of 72 USD while at or below 15 days. So it might start with this plan where we have a low cost and then adjust it so that it slightly favors lead time over cost, like maybe expensing on-time delivery as well. I believe that the current input data of this scenario isn't actually possible, but it gives a good insight into how it's going to tackle it. You can see here that's planning up to 25 runs to find the one that satisfies it best. This does take a little bit longer though.
So does it automatically decide how many simulations it needs to kick off, or there's like a fixed way to define that?
Yeah, this was defined in prompting, so
Okay.
it's not fixed. I think like if it got to 25 and maybe it was very near to it, it could decide that it's going to do one more. It's more of a guideline than a rule.
Yeah.
And do you think there's a world where it would be possible, for example, if there are delays and you have some unused capacity in, your factory, to then have something that can look at lots of different products and say, since we have delays on this one product and we have like some resources that are unutilized, you could reallocate those resources to this other product? Or do you think I'm just being too, like, that would get very complex for the model to handle?
Yeah, I imagine you could build this in. It'd be roughly a similar problem to this, except you'd be just adding in an extra dimension.
Got it.
Where if this is currently focused on just building one product, if
Yeah.
you were to build in like a second product, for instance, you might then have you'd have an extra set of like factories that like can produce this final product, or depending on like how your supply chain actually looks. And then you'd be able to allocate capacity between them. You might run the solver independently for each of them, and then you could have the model just tweak how it's going to split up this underutilized capacity. So you can see here that it's run many more optimizations. What it's landed on is this one that is unfortunately a little bit over $72, but did keep lead time below 15 days, or at or below 15 days like I asked. As you can see, a lot of them have ended up being roughly the same, and that's because there isn't a ton of depth to the input data here, so there is only so many ways they can actually solve the problem. But it gives a good insight into how it's actually thinking about and reasoning about this problem. I can actually show the different weights that it used for these, so you can understand how it was thinking.
This is so cool. I especially love the map. I think maps are always great because then you can see where the problems come from, but then you can deep dive into the details when you need, which is really cool.
Yeah, exactly. Let me move my tab over to the OpenAI API dashboard, and I can show you the trace for how I was doing this. You can see all the different tool calls that it made. Okay, now over in the dashboard, you can see that initially it was going to do its like 5 seeded optimizations. It also produced a hypothesis for each of these, so that when we're going back, we can look at it and understand what it was trying to do. So you can see here that it was trying to adjust time a bit more from the 15.5. So these are the different weights that it's bringing in. So it has cost at 1.4 at the moment, transit, which is speed, at 1.6. Risk maps to the on-time delivery. Oh, and there's also a CO2 weight, which we don't surface in the UI, but it's deprioritizes relatively. But here it's attempting to be more aggressive. Oh, actually, sorry, this is in reverse order. So these are the most recent ones. So if we go to the very end, that will show this will show the exploration a bit faster, which is the 5 seeded ones. So here it's just bringing in a bit of randomness, seeing how all of these weights impact the final solutions, so that it can understand it a bit more. And then here it's trying some extreme scenarios for maximum cost of very high transit. And then this is like roughly where it landed on to try and solve this exact problem. There's a few more here. So you can see that it kind of kept going on this to figure out if it could find a working solution. Risk maps to on-time delivery.
Got it.
Amazing. Should we, because I'm curious to see how much the model takes versus the actual LLM takes versus any other model it's being hit behind the scenes to run these optimizations. So can we deep dive into the architecture of the solution? As in how it is built behind the scenes?
Yes, of course. So you can hopefully see, first I'm going to start talking about ChatKit, which is what we're using for this chat interface, which can open it. The cool thing to see here is this client tools
for
feature.
my reference, what is ChatKit? What does it do exactly? What does it take away?
Okay. ChatKit is a new API product from OpenAI, which makes it super easy to build chat experiences like you saw in the supply chain solver. So this entire side pane piece, which had all the widgets in it and which was interacting with, this is all powered by ChatKit. First, I'll show how we built this. So one of the cool things with ChatKit is that it makes it really easy to maintain conversational state. So when you're building a chat experience, normally you have to manage taking all of the states and all of the context that's happened so far on the thread and then sharing this with the model and saving this per user. So it abstracts all of this away so that you can concentrate on just building the tools and the agentic experience like you would want to. So one of the cool features that we used here for this was client tools. So this makes it very easy to take actions on your front end based off of what's happening in the conversation. So one of the ones that we used here was opening the tariff modal. So when I asked it to show more details and it pulled up this screen, this happened through a client-side tool call with ChatKit. And it was able to pass all of these variables directly from the back end into the front end and then render them in a way that made sense. Another cool feature, which is actually controlled more on the back end side than the front end, was the widget. So where it was able to show that the price is going to go up by roughly $8. This came from the backend directly. So let me show this over here. This part is building up the widget using the backend. So you can see here that adding a row to it. It's adding a divider, and they invented kind of their own markup language for building components in ChatKit that you can render then in the chat interface. You can see this a bit as well with the apps SDK for ChatGPT that we launched recently. And then separately here is that tariff modal where it showed the more detailed view. Here's how we actually called the client-side tool, where we gave it a name, which we then invoke, which maps to the name that we have over here. Open tariff modal, you can see that we call the same thing. And then we gave it some arguments. So we told it, okay, which origin the tariff is coming from, and then what the percent is. And then this return statement is what's going back to the agent and agent's SDK so that it knows it is completed successfully.
Yeah, the TLDR is just building a chat GPT-like experience, but that's customized to your brand, your needs, etc. So just because we noticed that a lot of customers were building individually, like trying to rebuild some
Mm,
sort of like ChatGPT interface. So then we decided to build something that people can just use quickly.
makes sense.
Yeah, exactly. It makes it really easy to get up and running with like a custom chat experience. So for instance, if ChatKit didn't exist, the chat experience that I would have had in this demo would likely have been a lot more primitive, and it wouldn't have had these client-side tool calls and this type of thing, because that just takes a lot of work to build.
Mm.
And so having something that works out of the box quite simply is very, very powerful. And managing the conversational state in particular is one thing that just takes a bit of effort to get right. It's not a particularly hard engineering challenge, but having to do it over and over and over again just takes some time. So it's super convenient to have something that works out of the box. So this is diving more into Agents SDK here. So you can see here that we're defining function tools, which is essentially just a decorated function in Python that the agent can then invoke. And then lower down here, we can find a few different tools. I'll talk through some more of these later. But lower down here, we're actually just creating an agent using GPT-5. We're giving it a low reasoning effort in this instance because it didn't benefit too much from having a very high one. We're giving it its prompt, and then we're giving it a list of tools. To best understand how this works, we might just dive into the prompt very quickly, because this kind of explains all of it. Essentially, it's just telling it what it should do in all of these instances. In this case, we just run one single agent, and we could have done handoffs so that one could help model the tariff scenario and another one could help run the optimization. But in this case, it performed quite well as one singular agent. And I think that just for purposes of keeping things simpler, it made sense just to keep it as one. And so we gave it a few different flows that users might ask for. So in this case, someone asked about the tariff impact. Then we tell it that it should parse the percentage as an integer. So this is because we use integers throughout this. If the destination is not specified, just for the purposes of this demo, we assume South Korea because this was centered around South Korea. And it tells it to call the show tariff impact function. For it asked to optimize, this is like it's slightly more interesting. So first, what it'll do is it'll derive a base weights profile from the user's goal. So this is what I was showing earlier, where it has cost, it has the transit, it has, which is like kind of the speed, it has the risk, which is the on-time delivery, and then CO2. So kind of understand this natural language prompt and then turn it into these weights. It'll generate a few different distinct weight variants around this base. Tell it that it wants to have an evenly spread or a well spread set. So include at least one extreme example, and then several progressively less intense mixes. So the idea would be that if someone asks for the cheapest plugin, it'll produce one that only optimizes for cost, and then it'll produce a few less extreme examples so that then it's able to understand how these weights interact with each other. For each variant, then it calls the optimize function. And if the user asks to test a scenario, it should include it under constraints JSON under scenarios. So where we had the tariff earlier, it included this as a constraint so that the base solver understood that it had to model this extra cost into the completion. And what it does then is just some basic plumbing. So it tracks the return ID and the key metrics that returned by the model. So the cost, the lead time, and the on-time delivery. And then once it's done all of this modeling, it'll select the best run per the user's objective, and then it'll show the user the options. So this show user multi-op function just rendered that screen that we had earlier, which showed all of the different scenarios that it ran.
And so
Where
here,
it does,
it's when you say call optimize that you're going to trigger the traditional ML model that is going to do the optimization through this function.
yes, exactly. Let me go over to that really quickly so you can kind of see how this works. Here we go. So you can see here that these are the parameters that the model is passing in. So first is this hypothesis. The reason we capture this in the tool call is just so, like I was doing earlier, if we're running through the traces, we're able to see roughly what the model is thinking. It's useful for debugging, but not strictly required. And then we pass the rest of these in as floats. And then this constraints JSON just allows us to capture anything else that is important. In this case, it's just a tariff. And then there's also those baseline constraints that you called out earlier, like making sure that none of the factories are running at over 100% capacity, and also meaning that we have to have all the parts required for our manufacturing plan. So this is just some basic input sanitization. But if we go down to here, we can see that we're running our solver with the solve request. So we convert all of these into a JSON DSL, where the weights are really the most important thing. And then also the scenarios are put into it. And then our data set is the kind of simple data set that centers around Korea. And then we give it previous run ID as well if we want to track the deltas in it.
And so then to summarize, the model receives the data from the UI. It fixes basically the JSON and all the arguments. We need to go and hit this function with all the required data. And then takes the
Yes,
output
yes.
and reasons about what is the best run, basically, given the user ask.
Yeah, exactly. And it can do a follow-up run then if it figures that it's getting close to a better solution, then it might need to tweak the weights a little bit more.
Okay, cool. And this solver, where is it running from exactly? Where is it? What is it?
Oh yeah, so this is running locally.
Okay.
Let me this is like the side of things I'm not super familiar with, but it's a CP SAT solver, which is constrained programming plus like SAT hybrid. It comes from the Google Bower tools kind of package, which is great for all of these kind of constrained programming things. And essentially it's just a integer decision problem. So it introduces these constraints about, okay, we need to make sure we have the right amount of things. We need to make sure that things are manufactured in the correct order and that everything runs to a reasonable timetable. So it allows us to express through this like domain specific language what we're trying to get at here.
Got you. And then so in this case, we can represent, or if we want to generalize it a little bit, we represent any model you have in your business that, I don't know, you have built and you have fine-tuned and you have all your SME knowledge built into this model. You just call it to perform this scenario optimization for you. Like it can, in
exactly.
an abstract way, it can be any ML model, classic ML model. You just use it as a tool. You hit it through the model.
Yes, exactly. And we kind of find as well that in many cases, businesses will have these kind of classic ML models that they've already built and like trained upon over the years, but they have, say, human operators who have to go and tweak these weights or tweak these parameters to solve a real business problem. So it's helpful for them to be able to do this automatically, where like they might have a team of 10 people sitting there doing this for days to try and get to the correct scenario. It's like, okay, we can actually go and run like thousands of these in parallel to figure out that we actually have the best solution for the problem.
I love it. It's the first time I see a solution where we add a layer of like a reasoning model on top of, those optimization problems. It's very powerful. Yeah.
Yeah, exactly.
So I have another question then. So when we run these 5 optimizations in the beginning before, is it each optimization is one call to this tool, or in one call, it just by default, we let it run 5 times?
It's one call to the tool, but this is because we've enabled parallel tool calling. So the model is able to then interpret the query and kind of get an idea of what the customer is looking for, and then make sure that these first models are like roughly clustered around. So like say they want to get cost down. It's like, okay, we might do like one extreme example where all we care about is cost. And then we might have one where it's like, okay, like 80% cost, 20% speed, because it's more useful than just kind of generally having a preset like cluster that we put into it.
And this parallel calling is handled on the app layer?
It's a feature that's built into the OpenAI Agents SDK.
Oh, gotcha. Nice.
So you can like simply just enable it and then it'll go run like that.
Nice.
I wanted to ask as well about how do we ensure that the model's decisions are explainable and auditable, but you've already shown the traces. So I imagine this is how you would like do observability, or is there anything else that we need to highlight?
Yeah, that's kind of exactly it. So what we have, so when you have these traces, you can go in and you can see, okay, these are the weights that it selected and this is why. As well, at the end, it'll show you the run that it selected based on what it thinks you're looking for, but it'll also show you all of the runs that it did and the outcomes for these. And you can actually disagree with it and tell it, oh, I actually preferred like run number 3. One improvement would be that we could actually bring the hypothesis into this view as well, so that then the operator could understand, okay, this is why it made these decisions. Currently, this is only surfaced through the traces, but it would certainly be an improvement to bring it into the front end too.
Amazing. Are there any other features that can help these get improved that we haven't talked about?
I think that the main improvement that you'd make from this demo would just be to hook it into a production system. So currently the data set for it is very limited. So you kind of saw when it's running 25 examples, it's like, okay, maybe there's actually only 5 different ways of skinning the solution. Like once you actually add in the tariff, which makes it feel a little bit more hollow. And this is just because we obviously can't build a demo for showing everyone on real customer data. So like that would certainly be a pretty big improvement.
So in terms of how the customer you presented it to perceived it or received it, like what did they like about, even in the app, or what were they more triggered by?
Yeah, they quite liked this idea of essentially just being able to be relatively certain that they got to the right solution.
Mm.
The customer that I presented this to about 2 months ago, they're like super interested in this idea of going beyond supply chain as well. They had a few different problems where they just had like human operators trying to bring down a cost using an inbuilt model. And they're like, okay, this is super powerful. We want to roll this out very broadly across all of these different problems because like, yes, this demo concentrates on supply chain, but like, as you kind of identified, this like generalizes pretty well across all of these. So it's more just the flexibility of this, where all you have to do then is encode what a good solution looks like in the prompt, and then tell it, okay, this is like how you actually start doing it. This is like kind of what good looks like. This is how you understand the user's problem, and then just let it kind of go from there, and then you're able to see how it works. And this ends up being quite a good solution to a lot. I could generalize it very well.
Amazing things.
For every optimization problem, you
Yeah.
could like use this.
Yeah, even going beyond optimization, like optimization is the obvious one. I think that optimization, scheduling, all of these can be like reasonably improved by this type of approach. So I think what we realized when we initially set out to build this was that solving supply chain just using LLMs was not the right way of going about it, and because there's a huge amount of data that needs to be ingested sensibly. So we found was, okay, if you've got a very small data set, it might actually be able to produce a good supply chain solution where it's like, okay, we'll build these factories, we'll use these lanes. But as the data set grew, it was hard to reason with all of this in context and then actually encode. Like I think the classic example was that LLMs aren't very good at math, and this is like a GPT-3 problem that is now solved through reasoning models. But just kind of trying to, it's like when there's so many different solutions, it was hard to figure out, okay, this is the right way of doing it. So we realized then was, okay, maybe we should take a traditional ML technique to this, and then give the LLMs an interface to try and improve upon that solution. And then this ended up working.
Amazing. Thank you.
Thank
Thanks,
you.
Owen.
Yeah, thank you.